Morning, everyone. I'm Nakajima from High-Tech Inter, Tokyo, Japan. And I'd like to talk about the ultra-low delay and the resilient multi-channel video encoder for efficient remote construction. The first is introduction. Japan's working age population is decreasing by 20% from 2020 to 2040. And so the Japan's Ministry of Land, Infrastructure, Transport, and Tourism introduced the I-Construction 2.0 strategy, which aims the labor reduction by 30% by the increase of productivity through the introduction of the automated construction by 2040. So in the course of the automation in construction, the remote construction is one the pivotal step towards the automated and autonomous construction. So in this presentation, I would like to talk about the development of multi-channel video encoder for the remote construction. And we have conducted the experiments across 5 types of wireless networks and demonstrated that the ultra-low delay codecs support the adaptive remote construction architectures tailored to each network. So this is a typical remote construction configuration. And we think that there are 4 issues. One is implementation, second one is video transmission, and the third one is the wireless communication, and the fourth is the transmission of control signal. So I will talk about each of them. So as for the implementation, it still requires the high expertise for installation and setup for remote operation systems. So one of them is that, for example, 4 video cameras and 4 encoders may be required for the situation understanding. So if we can have a 4-channel video encoder, then it can reduce the cost and space, as you can see in the figure. And the second one, the video transmission. As for video transmission, there are 2 major issues. One is end-to-end delay, and the second one is coding bitrate fluctuation. So in the remote construction, the low delay and the stable video transmission is required for the efficient operation. The third one is the wireless communication. There are 2 things. One is the communication network quality. First one is transmission delay. The previous slide, I talked about the codec delay, but in this case, the network delay. The second, jitter and packet loss, and also the bandwidth fluctuation of the network. So we need to select the appropriate network according to its performance. The second one is wireless network itself. There are various kind of broadband networks these days, like 5G, private 5G, low Earth orbit satellite, LEO satellite, and mesh Wi-Fi. So in each scenario, we need to construct error-resilient network by such methods like ARQ and FEC. The fourth one is the transmission control, transmission of the control signals. In many cases where the video is transmitted by Wi-Fi and the control signal is transmitted by the other networks, such as specified low-power radio, which may result in a complicated system. So if the video data rate is strictly controlled, then we can integrate both video and control signal. So we have developed the multi-channel ultra-low delay video codec and solve the issues described before. So the table one shows the main issues and solutions. The first one is the codec implementation. We have developed a 4-channel video encoder based on 4K based one-channel video encoder. So as for the remote construction, we think that high vision, high definition video like a 2K video is enough, but we need 4-channel for each construction machine. So we have developed the 4-channel video encoder, 2K for each. And the second issue is coding delays. So as you may know, there are coding standard like MPEG, and MPEG use a variety of coding modes. So here I show you the coding mode like intra, which coding by itself. The P is predictive coding. It uses the previous frame to predict the current frame. And the B is a bi-directional frame, which use the previous frame and the future frame and combine to predict the current frame. So as in terms of coding efficiency, I plus P plus B structure is better than the I plus B, P, because of the higher coding prediction efficiency in IPV structure. But in terms of the coding delay, the IPV structure is takes time because of the prediction scheme. So in this case, the IP structure has a lower delay. And the another issue is that the data size. So iframe has a very big data size, and second one is a P, and the third one is B. So in this case, IPV structure is the data size variation is very big, and the IP structure is less than that. And in the IP structure, there's another mode which is called intra-slice. So in this case, all the frames except the first one is using the P frame, and each frame has a refresh slice. So we have done the experiment of the video coder, and we found that when we employ the intra-size, the average bitrate is higher than the IP structure, but fluctuation is less than that. When you look at the figure 10 and figure 11, you can see that figure 11 has a smaller fluctuation. So we also have the experiment using the 5 types of wireless networks. One is wireless for robots, which is used for UGV in Japan for about 10 years. And the second one is mesh Wi-Fi. Third one is public LTE. Fourth one is private 5G. And fifth one is LEO satellite, Starlink. So we have experiment about this field. We employed a relatively simple task, moving and around point A to point D. So the transmission experiment was also carried out. And as for throughput, the 10 to 50 megabit throughput can be obtained in 5 types of networks, and the delay is about 4 to 80 milliseconds, depending on the types of network. And end-to-end delay, which means from video camera to encoder network and the video decoder and the monitor. The end-to-end delay is about when ARQ is off, 160, less than 160 milliseconds, and when ARQ is on, it's a retransmission scheme. It's about less than 260 milliseconds. And the former study shows that less than 300 milliseconds end-to-end delay was realized. In that case, the efficient remote construction can be done in this scenario. So we found that even in these networks, we can employ the less than 300 millisecond end-to-end delay. Okay. So when you compare the error regime,
I will have to ask you to wrap up. We're over the 10-minute mark.
Oh, okay, sure. Okay, so this is a comparison of the ARQ effectiveness. Okay, conclusion in this paper, we show the multi-channel ultra low delay video encoder employing the 5 types of networks. And we found that less than 300 millisecond delay can be achieved. So we think that this kind of ultra low delay can be applied to the remote construction. And so that's all. Thank you very much.
Thank you very much.